Hello guys, welcome to the second part of the third video. I'm sorry that I just putting these parts right now because my life is a little bit busy and I'm doing a lot of stuff at the same time. So I'm trying to manage everything together, but it's a little bit tough, but it's okay. So enjoy the video. Okay, so now we basically have everything that we need to start the main time loop. Okay, so for a flow, we basically have to specify the boundary conditions. So in our case, we have to specify the inflow boundary condition, the outflow boundary conditions, and the conditions on off. For example, in our case, in the example of the theme place, we have we could have two plates, like if the flow is passing inside a channel, but in our case we have periodic boundary condition in the y direction, so we doesn't need of a condition applied explicitly. Okay, so this is applied by the periodic boundary conditions that I will show in just a moment. But we have to define the outflow boundary condition and the inflow boundary condition. The outflow boundary condition is basically this one. We take, if we look to the final part of the simulation, imagine that the simulation ends here. Okay, so these points is inside the fluid domain, those points here. Okay, but according to our grid model, each point of those, it has velocity vectors that are pointing to 3 points that are outside of the domain. Okay, those 3 points here. So basically, to define our outflow boundary condition, we have to say which are those points here. Okay, so I think that the simplest way that we can define those is to say that those points are those that comes from the the last nodes before them. So we just repeat those 3 nodes here outside. So this is this outflow boundary condition. Okay, again, inside the loop we have to, once that we have the distributions f in, we have to calculate the density and the velocity. So this is this line. Now we have to define the inflow boundary condition. So basically, in the inflow here, we are imposing that velocity that we show in the beginning. So here is in x equal to 0. So this is this expression. Okay, so these 2 dots here from numpy means that we are taking from all points, in this case in the both directions, x and y, in x equal to 0, and these 2 dots here means that we are taking in the whole y points in x equal to 0. So we have a lot of points here. Okay, y, so this is represented by we take all those points by just putting those two dots here. Okay, so this imposes the velocity in the beginning of the channel. The density on those points, again, it has the same problem of the outflow boundary condition, because we see that we have to sum over the depth in from a given cell to calculate the density, right? So the problem here is that in the beginning we doesn't have the points that are outside of the first points. For example, imagine that we have 3 points here. So to calculate let me erase this part too. To calculate the density of these points here, this point in the middle, we have to sum over all those 9 values here. Okay, So, but basically we doesn't have those three that are outside of the domain. So use a technique that is uh, it is known as the Zohri boundary condition for the density. I won't go into the details of how it is, at least not in this video, but it's according to this expression. It's a quite simple expression. In a further video we can explain this in a more detail. And again, inside the loop we have to calculate the equilibrium. This will be assigned to this value Fx. Now that we have the equilibrium in all the points, we have to assign again a value to those 3 points that are outside of the domain. Again, this is a trick that I think that it was first made by Jonas Lattice and other professors, or I don't know if it was made by Zohri also. I will check that out. So here we have the collision step, that is that part here, right, that we just write. So this is where the particles are colliding to each other, and then we will know which particle should go to where in the simulation. Okay, so this is the BGK collision operator, and here is the bounce back. So this is the way that the particles are interacting with our obstacle. So if we have an obstacle here, so the particles that are coming with a given velocity that will encounter this obstacle, they have to come back with the same velocity. So basically this is the bounce back. In this case it will be the full wave bounce back. So we just take the particles that are coming with a direction I, and she has to turn to the opposite direction. So this is the first array that we show in the beginning, one of the first ones that I said it was created for this trick. Okay, and here the values where we will do the bounce back are the values defined by the obstacle. That is the thing place that we define in the beginning, also in the function definitions. And in the last part is just the streaming process. So we have to propagate each particles for a given direction. Okay, so I think that the video already stayed a little bit big, but I think that we show basically everything from the code. I will probably run the simulation and put a video together with the video when I publish it. Okay, thanks guys, bye bye. And now I promise that we are going to show a video of the simulation. So I prepared a new simulation with a little bit higher resolution of the theme plate. So here it is. So it has 2000 points in the x direction, and I think it has 800 in the y direction. So here you can see the von Karman vortex street. Let me take my can out. So yeah, this is reproducing quite well the physics of this situation. So I hope you guys enjoyed, and I see you guys in the next video.